Hello everyone. Today we are starting chapter 5 and in this unit we're going to solve a lot of these, or we're going to do a lot of these lessons with lesson style, where I'm going to give you the notes for homework, and then when we get into class we're going to practice the skills that we're learning. One reason why I really love this chapter is that it combines everything we did with chapter 3 with graphing and everything we learned in chapter 4 with writing. And so we're really going to be able to put those two concepts together and build. In this lesson, we're going to be talking about systems of equations, and we're going to be talking about solutions and graphing for this first lesson. For our warm-up today, I want you to think about which equations or which lines does the point 2, 4 lie on. And we know that if a point is a solution to the equation, then it lies on the graph of the line. So if I were to determine algebraically which lines contain the point 2, 4, I would substitute for 2 in for x and 4 in for y for each equation. It would be helpful if I substituted the right number in. And if I ended up with a true statement, then the point would lie on that line. So as you can see, the first line does contain the point 2, 4. And again, I am using my order of operations here, so that's something that's always in effect. The second line also contains the point 2, 4. The third line is in standard form, but it doesn't change the way that we would approach this problem. This third equation does not contain the points 2, 4. So as you can see, it does fall on lines A and B. And this is what we call, or what's going to happen to these lines. We're going to find out something about this, and it's going to tie into our system of equations. So a system of linear equations is a set of 2 or more linear equations in the same variables. This will especially come into play if we're looking at word problems, which of course we will. And a solution, which ties into our warm-up, is an ordered pair that satisfies both equations in those variables. So if we have a solution to our system of equations, it must be an ordered pair that's a solution to each equation. So our example is from our warm-up, is that 2, 4 is a solution to the system. And sometimes when I write a system, I use curly braces. Y equals negative 2x plus 8, and y equals 1/2 x plus 3, because it lies on both lines. It satisfies both lines. It's a solution to both equations. You can kind of think of it in all those different ways. So that's step 1. If I give you an ordered pair, can you tell me if it is a solution to the system? So we're going to do that twice. Go ahead, you can pause the video and try these on your own, or if you want, you can just follow along with me. So for the first set of equations, I'm checking the point 2, 0. Just make sure you're substituting things in correctly. Right, so we noticed that the point 2, 0 is a solution to the first equation, but that doesn't necessarily mean it's going to be a solution to the system unless it also satisfies the second equation. So it does not. So no, 2, 0 is not a solution to the system. It doesn't satisfy both. Okay, let's try the next one. Let's try 1, 3. Again, 1, 3 works in the first, solution to the first lies on that line. And yes, it looks, it also satisfies the second equation. So 1, 3 is a solution to the system. So you can't just tell me yes or no, but you have to confirm and show me that it does solve both problems as a solution. And this would be a way that you can check your answer when we're doing our next part. So at this point, I just gave you points and you were telling me if they were a solution. So now the question is, how do we actually solve a system? What if I didn't give you an ordered pair? There's actually 3 ways to solve a system of equation, and each way has some pros and cons. The first way that we're going to talk about is solving systems by graphing. And so if we think about our lines, okay, I'm going to actually pull up a Desmos very quickly. And I'm going to show you how to do this on your graphing calculator in class. Right, and then our first line was y equals negative 2x. I believe it was, I want to say plus 8. And then our second equation was y equals 1/2 x plus 3. And remember how we said in the warm-up that 2, 4 was a solution? So I want you to look and see what's happening here. What do you notice about the point 2, 4? Well, hopefully you noticed it here. It's where the lines intersect. And so one way to solve a system is to graph each equation, see where the lines intersect. And so we're going to graph these by hand. Remember, this is our slope, and this is our y-intercept. So the first line, we're going to start at 8. A slope of negative 2 means we go down 2 and right 1. And then our second line, I'm going to do a different color just so we can kind of get some contrast. Our slope is 1/2, our y-intercept is 3. That's not super accurate, but there is our solution, point 2, 4. And I'm not going to check that because we already checked it in the warm-up. But for the other ones, we're going to check. Now, both of these lines were written in slope-intercept form, so that's the method that I used to graph them. But just a reminder is that there are other ways to graph equations. So let's take a look at example 2. This first equation is in standard form. I could, if I wanted, put it into slope-intercept form, if that's the way you like to approach graphing, and that works. But sometimes it's actually easier to find the intercepts. And so remember, to find the intercepts, we set the other variable equal to 0. So hopefully you can quickly tell that this equation has an x-intercept of 3, and actually the same thing will happen for the y-intercept. My second equation is already written in slope-intercept form. The coefficient of my x is 1, so that's my slope. My y-intercept is 5. Okay, so because my first line was not super accurate, it does not look like my system is going to be beautiful. So let me go back and regraph that. This is why we use a ruler when we graph. There it is. So our solution is -1, 4. So let's do a check. Does -1, 4 solve the first equation? So is 4 is y. Is 4 plus -1 or 3? Yes, it is. Again, I'm just using the colors to differentiate what's happening here. And then for my second equation, does 4 equal -1 plus 5? It does. So there's always a way that I can check my answer. why don't you go ahead and try the third one on your own and then come back and watch the video. All right, so for this last one, I'm actually going to put both of these in slope-intercept form. The first reason why I'm putting the first equation in slope-intercept form to graph is because my x-intercept would be 8 and my coordinate plane doesn't go up to 8. My second one does not have a very nice x-intercept, and so that is why I'm going to choose to also use slope-intercept form. So remember, to get something into slope-intercept form, I'm going to isolate the y. So my first equation has a y-intercept of 4 and a slope of -0.5. Again, yours will be a lot more accurate than mine, which will be wonderful. So remember, for this one here, the second equation, we really have to pay attention to our negatives. And a negative divided by a negative is a positive. So we want to remember that. So my intercept is -4, and my slope is 3 halves. And my solution is 4, 2. Again, I don't have a whole lot of space left here. If I were to think about this, is 4 plus 2 times 2 equal to 8? Yep, 4 plus 4 is 8. Is 3 times 4 is 12, minus 2 times 2 is 4, so it's 12 minus 4, 8. Yes, it is. So as we can see, it's nice to solve something by graphing because we have a very clear visual of what's happening to the two equations and where they intersect. There are some other methods though, and we can talk about the limitations of graphing when we talk about those other methods. So great job. When we get back into class, we are going to practice some solving systems by graphing.